All right, welcome everybody to this webinar. We will start in about a minute or two to let folks get in and get comfortable as we get ready to get going here. All right, and as you're joining the webinar, just to let you all know up front that if you have any questions, please use the Q&A function to ask questions. We'll be keeping an eye on that, and we are more than happy to answer questions while we're giving the presentation. So do not feel like you need to wait till the end. If we're talking about a specific thing and you would like some clarification or have a comment to add or whatever, please, by all means, use the Q&A to drop something in the Q&A panel for us. Okay. All right. So let's get going. This is a webinar on the current and future state of running Java apps in the cloud. And today we are very excited to have a good friend of mine and a wonderful human, very smart human too. He just wrote a great book called Optimizing Cloud Native Java. Ben has written many, many books, but I'll throw it over to Ben to let him give a quick introduction about himself.
Thanks, Pratik. It's great to be here and nice to be back on the podcast. So I have been interested in architecture and performance for a long time. My current role is that I'm a senior principal at Red Hat, and I am responsible for observability within the Cloud Native Runtimes group. So that basically is things like Quarkus, which we're going to talk about a bit later, JBoss EAP, and all of the other runtimes products that we have. So not just Java, although the majority of what I do is Java based. The book's kind of interesting because it's badged as the second edition, but there actually never was a first edition optimizing cloud native Java.
Yeah, I was wondering about that. I was like, I don't remember reading
Yeah,
this book, Ben. Like, why is this a second edition?
well, because here's the real first edition, which was just called
Ah,
optimizing
yes.
Java. And if I like kind of lean back, you can probably see back on my wall here. I actually
Oh,
have a
yeah,
copy
yeah.
of the cover. And it's kind of interesting because obviously, these days everything we do is in the cloud. We're long past that tipping point. But when I wrote the first edition with our buddy Jim Goff, it was still the case that we were thinking about single JVM performance largely. And I think part of the story of this book is that transition from moving from thinking about the performance of an individual VM or an individual host
Yes.
to a clustered and a cloud-based application. So that's why the change in title as well. So it's a bit
Nice.
strange to call it a second edition
Yeah,
when there was no first edition, but
yeah.
I think it kind of works.
Yeah, absolutely. And I think you bring up a really good point there, which is, a lot of people, everybody, it feels like has moved to the cloud or is moving to the cloud. And, for Java developers, going from thinking about a single process running on the machine to multiple processes or running in environments like Kubernetes or cloud functions or whatever, there's quite a bit to consider when it comes to performance. Speaking of performance, we also encourage you, aside from going and buying Ben's book, we also encourage you from looking at Azul's Cloud Cost Optimization for Java Workloads ebook. It's a free download. We spent a whole bunch of time working on it. We have our folks from engineering and other people within Azul who put together this wonderful guide to help you figure out how to spend less on the cloud. And as everyone knows, everyone is trying to figure out how to keep cloud costs under control. And this book is a great way to get started to understand some of the topics for that. So please grab that also and make sure you buy Ben's book. All right,
Thank you.
so this is what we're going to loosely cover today. Ben and I have a full artistic license, I think is the right way to put it, to take the conversation in a different direction. But what we wanted to cover are some of the basics of starting a Java app, and then we'll talk about like how that looks a little bit different for cloud workloads and resource constrained workloads. resource constrained environments as opposed to just running bare metal, which is what we used to do. We'll talk about like a few of the lower level things, like native compiled versus AOT or ahead of time application, CDS, class data sharing, and then we'll get into the meat of some of this, how this actually looks and works in the cloud and explain. And then we'll look to the future with something called Project Leyden, which is something that's been brewing for a while. And we'll give you some insight as to what's happening there. So let's talk quickly about JVM startup. Most of you who are longtime Java developers know that there's approximately a few large phases when you start a Java application. Obviously, the JVM itself starts up, and once the Java virtual machine has started up, it starts loading classes. It does basic initialization, for example, for static initializers. And then it starts executing your bytecode, right? Takes your jar files, unwraps them, loads the class files, and then most people today use a framework like Quarkus or Spring Boot. So that framework needs to initialize, and then your app is ready to service requests. So Ben has put together this nice diagram on exactly what happens. I kind of talked about it in bullet points, but we'll look a little bit at this just to give you an idea of like kind of what it looks like, and then we'll fit this in to how this can be leveraged, or your understanding of this can be leveraged to do faster startup and performance stuff in cloud environments. So.
Right.
Yep.
So basically, what we have here is there's actually quite a lot going on in this diagram. So I think it's good just to take a minute or so just to pull it apart a little bit. On the left-hand side, we have the development time process, which leads to the generation of a class file. Class files, as I hope everyone knows, are machine independent. They're bytecode. They're not real machine code that would run on an actual processor. They are an independent, or sometimes in compiler theory called an intermediate representation. Which is then used to turn into something which can be executed on Linux or Windows or Mac or Solaris or whatever, wherever you want to run. So that's the first piece. So when people talk about Java as a compiled language, that is the source code compilation. There's another sense in which Java is a compiled language, which is different to that, but we'll come on to that. So what we're going to focus on today is the right-hand side of this diagram, which is the runtime behavior. This is about execution of processes. And there are actually, I would say, four main processes which go into a Java runtime. And this diagram actually shows three of them. It shows class loading, it shows Java bytecode interpretation, it shows JIT compilation, and then there's the fourth one, which we don't show here and we're not going to talk about today, which is garbage collection. Not because
Yes.
garbage collection isn't fascinating, but just there are only so many hours in the day. Okay.
That's right. Garbage collection. We could spend the next hour or hours talking about GC. So
Hours.
we're gonna
We're not
we're
going to
gonna
do it.
we're not gonna do that today. But both Ben and I have some good presentations on garbage collection. So if you do a search for our name and Java garbage collection, you'll find videos by both me and by Ben talking about this stuff. Now, I think one thing I want to mention here is there's JIT compilation in here. And for those of you who may not be familiar with this, JIT compilation is basically the part of the JVM which goes and optimizes your code to make it run faster. And we're not going to get into that in much detail here either, because again, that's also an entire discussion unto itself. Let's press forward and talk about native compiled and AOT. So if you're not familiar with what AOT stands for, it stands for ahead of time. It's basically a way of doing work that you would normally do when the JVM starts up and the application initializes. And then, of course, there's native binary, but I'll let Ben say a few words about both these things before we talk about the other topics and how this fits into the larger topic that we're going to talk about in a few minutes.
Right. So this is coming back to the point that that Java is a compiled language in another sense. On the previous slide, we saw how the JIT compiler worked, and JIT stands for just in time. The other name that you can use for that is runtime compiled. So it does produce machine code. It does convert your bytecode into machine code, but it does so on an as-need basis. It only converts to machine code the parts of the application that actually warrant it. And so it's like a trade-off. You spend the cost of compilation at runtime, but only for the important parts. Whereas in a C++ or a Rust application, you compile everything to native code, even the parts that don't really matter that much. So there's a trade-off being made. Now, for Java, when we do AOT compilation, what we're doing is it stands for ahead of time. So if you're a C++ or a Rust programmer, AOT compilation is what you think compilation is. But in a Java runtime or .NET runtime, JIT compilation provides an alternative view of that. And this is something that we're gonna have quite a lot to say about, because the balance between these two and the fact that it isn't choose one versus choose another, but increasingly it's choose both. And how do you choose both in a smart way in order to operate effectively in a cloud environment? That's really where the future discussion is going. Um,
Yes, absolutely.
so for example, the best example I think is the Graal compiler. And again, huge subject, could say so much about the Graal compiler. It's super interesting. But inside the JVM, inside Hotspot, we have a couple of compilers, the C1 and the C2 compiler, both of which are implemented in C++. Graal is a new compiler that came out of Oracle Research 7 or 8 years ago, maybe a bit more.
Yep.
But it's actually implemented in Java itself. Now, and this might be a slightly brain twist, but because it's implemented in Java, it runs on the Java interpreter, but it is itself a JIT compiler. So the first thing it does is it takes the classes which correspond to the JIT compiler, and it JIT compiles them. So literally the first thing that Graal is capable of doing, it turns out that in practice this isn't like a super efficient way to do this, but it's possible. And it basically compiles itself. And then after that, it can start to compile up your application. So it's a very interesting approach. There's lots of super cool computer science. If you like to geek out about compiler theory and stuff, Graal has got so
Yeah.
much in it. But it's the basis of the Graal VM approach. And also, I believe that the Graal compiler itself is coming back to OpenJDK now.
That's right.
So this is a way that we will produce not only a JIT compiler, but it also has the ability to operate in AOT mode as well. So this means that you take a Java application and you convert it fully to machine code before anything starts to execute, and that will leave you with a package or a Docker container or something which is already compiled fully into machine code and will be able to be run somewhere. There's a couple of things
Yep.
which I think are very important to say about that. First of all, if any of you are Go programmers, you know that Go has a runtime, including a garbage collector. And it's true that native compiled Java programs would also have a runtime. It just wouldn't be as full featured. It would still have a garbage collector, but it wouldn't be as full featured as Hotspot or another Java runtime. The second thing is, and this again is sort of a long-term trend, which plays into a lot of what we see as to how the Java world is changing. Java was sort of presented in the old days, back when dinosaurs walked the earth, as a compiled language like C or C++. And that was a deliberate marketing decision. Actually, Java is not that compiled. Java is a very dynamic language. And in fact, for those of you who are super old like me, the Java runtime and the Java approach to many things is closer to a language like Smalltalk than it is to C++. There's a lot of dynamism in terms of the class loader, which we can see on the diagram here. New classes can be added to a standard Java program at any time. You can generate your own class loaders. You can load classes, days or weeks or
Yeah.
years.
Yeah, you can do dynamic class loading, and of course, there's the ability to basically have different class loaders with different class hierarchies and all that kind of stuff. That's how, for example, OSGI works, right? It uses multiple class loaders to bootstrap everything into a single JVM. So it is quite you're absolutely right. It's not necessarily just like kind of compilation and like static. It's very dynamic. So what one? Yeah, go ahead, Brett.
Yeah, so basically, this idea that you can have all this class loading and especially also reflection, where you can basically do tricks at runtime. You can call methods without having to write Java code, which actually is statically checked and compiled. You can just say, oh, I think I want to call the toString method on that object over there. And you can do it by specifying the name toString in a reflective call, or in the modern API, the method handles API. But those are, again, very dynamic. So the
Yep.
question becomes, well, if you're going to do ahead of time compilation, if you're going to produce a binary, you have to provide hints about what reflection you're going to want to do later. because
That's right.
that's really one of the sticking points is that we have this wonderfully dynamic platform, but if we want to actually do ahead of time compilation and to do things to do with startup time, we are going to want to in some senses constrain that dynamism. We're going to want to say, okay, well, I'm packaging my application and I know it doesn't need to do any more dynamic class loading. So why am I
Yep.
paying the runtime costs to have all of this wonderful dynamism which served us so well in the past? Maybe I don't need to pay that with that resource cost. So
That's
there
right.
is. Go ahead.
Yeah, what I was going to say is that if you're, a longtime Java developer and you've written any code that uses reflection, one of the things you quickly learn is that reflection is very costly and very slow. So it has a big performance impact in a negative way. So you generally want to try to avoid doing that. That's why typically only framework builders, use reflection to build out advanced framework features. So, and actually, there's one other thing I wanted to mention. Maybe you can clarify a bit. So if you're running, for example, Graal VM, one of the limitations is that you typically don't have access to reflection at runtime, which causes issues with certain libraries, right? Is that approximately correct, Ben?
Yeah, that's right. What you have to do is you go through and you run it and you make a list of all the things that you're going to need reflective access to, and then you provide it, and then it provides you with like only those methods will be reflectively called. So it removes the unlimited reflection capability, and removes what we call the open world, where you can class load
Yeah.
anything and you can reflect anything, and it brings it back into this tightly constrained environment which we call the closed world. And those are terms which I'll come back to when we talk about Project Leyden. Um,
Yep. All right.
so
So anything
one,
else before? Yeah, good.
yeah. Just so basically, one other thing that I want people to keep in mind, which I think is important, is the distinction between an outcome and a mechanism.
Mm,
Okay. So an outcome is reduced startup time or reduced resource utilization, right? Those are goals. They're things you're focusing on that you want to achieve. The mechanism is how you get there. And one mechanism for reduced startup time or reduced resource utilization might be ahead of time compilation. But sometimes people focus on the mechanism rather than focusing on the outcome. And I think it's
absolutely.
important to separate the two out and think, well, what is it I'm trying to achieve? People say,
Absolutely.
I want AOT compilation. Well, do you, or do you just want faster startup time?
Exactly right. What is the actual goal that you're trying to do? The mechanism is different from the actual thing outcome that you're trying to go for. So Um, and one of the things that's actually this has been around since Java 10, application class data sharing, hasn't it? It's been around for a bit, but basically it's a feature to enhance startup time and reduce memory footprint by sharing a preloaded set of classes among multiple JVM instances. Now, I'm trying to think if there how widely is CDS currently used? Uh, I think like uh can you do app CDS with Quarkus and Spring Boot currently? I can't remember if
I mean,
there's
so there are different pieces to this. So there's CDS within the JDK itself,
right, of
and then
course.
there was application CDS, which also then bundles library and application classes as well. Um, but again, we want to see this as a sliding scale. At one end, it's like load dynamically everything and recompile everything every single time, which obviously is you're paying that resource cost every time the process starts up. Now, we could imagine going all the way through to the other end where and sometimes people ask this, why don't you just save the machine code after you've done JIT compilation and reuse it next time? And that is an idea which is compelling, but it has some complicated aspects to it, as I know that you and the folks at Azul know well, with things like
Mhm.
Platform Prime. But there are some things that you can do, which don't go all the way there, which could still be valuable. I mentioned, for example, there are two JIT compilers by default in OpenJDK. There's C1 and C2, and it's probably helpful just to explain the difference between the two here. C1 is a pretty straightforward, it's a very simple JIT compiler, which does basic things. But what's important about it is it does things which are known to be safe. Whereas C2 is an aggressive compiler. it will do things which are potentially unsafe. I mean, it will never execute any code which is incorrect because it will always check before it uses its aggressive optimization. But what that means is it will potentially optimize and de-optimize if it's made a mistake. So the performance can be a lot more jittery. Whereas with C1, it knows the code that it's produced is sound, and it will never de-optimize it. So you can, for example, imagine a place along the sliding scale for class archives where you have something which contains C1 compiled code, where you could create that on one run, a training run, say, and then bring it back for subsequent runs. So AppCDS is this. It's kind of a moving target. It's still, I think, underutilized. I don't think enough people use it, but I think that at the moment it still has too much of a almost high touch component to it. There are still too many folks who don't feel comfortable doing the things that AppCDS needs to really get the most out of it. Now, it's great for the folks who are super performance junkies and are prepared to read up on how to drive AppCDS to get that last little bit of performance out. But for many people, I think it still needs to be made easier to use and to kind of be popularized and brought into the mainstream a bit more.
Okay. Yeah, I totally agree with you. Let's kind of dive in a little bit more. And there's a bunch of bullets on here, but of course, we're happy to share the slides. But instead of going through like kind of the low level differences between Spring Boot and Quarkus, I think what we'd like to do is talk about like the standard way of a JVM and framework startup and like the new cloud way. So let's start with this one. Just to give you an idea of like, when a JVM starts up and you start up a Quarkus or Spring Boot application, what happens, and then we'll switch to kind of the fancy new way of thinking about this.
Yeah, so I mean, this basically is your, like, I guess, oh God, it's probably this is your grandfather's these days, your grandfather's Java application.
That's right.
So you start up and the JVM process comes into existence, and it's just a standard Unix process with some extra tweaks because the Java way of thinking about a process is a Unix process, but it also has some additional special things about it. So, for example, the Java heap is a contiguous chunk of memory within the process heap, and things like that. You load your application. So in this case, this will be the jars that correspond to your app, and those will be loaded into metaspace, which is an area of the C heap, the process heap, which is outside of the Java heap. And that will be loaded in. The code will be read. It will start to bootstrap the application, and then we'll move into the middle box here, which is the warm up. So things are now starting to execute. Your application is responding. It's executing bytecode, but it's still getting into its steady state. So things will be JIT compiled in this. The JVM will figure out what the hotspots are, hence the name, and
Yep.
then it will compile them into machine code. So in this warm-up phase, the app will become more and more responsive until it reaches a steady state. This is where essentially all the hot paths in the code have been found. Everything which is important has been compiled, and we are at peak efficiency. And we will
Yeah.
stay there for as long as the process stays alive, and then we will shut down. Now,
Yeah. So
notice.
sorry, real quick, Ben. I was just going to interject here for those folks who may not be familiar with some of the stuff that you just said. When we say hot, that means parts of the code that can be that are not operating as efficiently as possible. So we call those hotspots because that's basically the slow parts of our bytecode execution. And so the JIT compiler will go in and look at those and apply any of, I don't know, hundreds of different optimizations to make that code run faster. So for example, one thing is an easy one to understand is something called method inlining. So if the JIT compiler notices that you execute the same branch of code and almost every time you call this method, it returns the same result, or it will inline that method so it doesn't have to put it on the stack and then pop it off the stack, which saves a little bit of time. But if you execute something like that millions and millions of times a minute, it all adds up and it all becomes faster. And the standard one is called Hotspot. Azul has its own proprietary JIT compiler called Falcon, which is even more aggressive at optimizing code and making it run faster. So anyway, just wanted to give a little explanation for those folks who may not be familiar with how some of that stuff works.
Yeah, I
And
mean,
one
I
more
think
thing, real quick. One more
sure.
thing, real quick. And there's a little bit of a maybe not trivia, but if we think about, like, let's say you have a standard Quarkus or Spring Boot application, maybe 20,000 lines of code. A lot of people don't realize, Java developers don't realize that as to how long it may take for that application to go from warm up to steady state, i.e. near peak efficiency. Depending on the application, of course, there's a bunch of assumptions here, but a standard application with 10, 20,000, maybe more lines of code can take anywhere from a few minutes to 15 minutes to reach peak efficiency, because the JIT compiler has to see that code getting executed, and then it looks at the different algorithms and optimizations it can apply to make that run faster. So it doesn't happen immediately. We'll talk a little bit about how that like kind of weighs into a cloud environment on the next slide. So
Yeah. So just to finish off, yeah, so that's a great example, Pratik. I think, let's for example think about a record, right, in Java. You have getter methods on the records. You don't have direct access to the fields, but that doesn't matter because you know that the record class is final. So it
mm,
can't be the case that the getter is overridden. So there's only one definition of the getter. So the JIT compiler can know with absolute certainty that you can inline the getting of the field and replace it with a direct field access. So that is my classic go-to example of an inlining. And that also is a great example of a C1-like optimization. So the C1 compiler, for those folks who are a bit long in the tooth, it's sometimes called the client compiler. And the
mhm.
old name for C2 is the server compiler. So if you've ever seen minus client or minus server, that's what that means. Whereas the other example is what's sometimes called monomorphic dispatch, which is where you go through a place where a method gets called, and it's always the same type. So it's always it could be, oh, I don't know, a call site where it's a class which has a subtype, and you notice that it's always the subtype and it's never the parent type. So what you
Right.
can do is you can make a speculative assumption to say, hey, I think it's always going to be the subtype. So what I'll do is I'll put in a quick little check which just says, are you still the subtype? And then I'll branch directly to the subtypes method. And that example is not guaranteed because something else could happen. You could see some other code path which meant you got to see the parent type, or another subtype could be loaded, and then that assumption would break. So that would be an example of a C2 optimization, which would then be backed out and moved in again. So all of this is part of the distinction between the two compilers. One other thing I just want to say before we move on is that notice that what we're doing here is we are, to want for a better word, amortizing the cost of JIT compilation over the lifetime of the application. Now, if you come from a world where you rebeat your Java application servers once a week, the cost of JIT compilation is trivial.
Very
If
low.
you
Yep.
if you are in an AWS Lambda sort of situation, it's not. So that relates very strongly to the fact that within the cloud we may have much shorter running processes. So the relative cost of the traditional way of building Java applications in this steady state approach changes based on the cost model for cloud.
Right. And as developers and DevOps people, we need to think about that. So let's actually go and talk about the more of a cloud environment here. Uh,
Yeah. So
so
basically,
yeah,
what
good.
what we have here is a recognition of the way that we deploy software and the way that it's changed. So these days, what we do is, well, people may have heard the expression livestock, not pets. Back in
Right.
back in the old days, kind of 20 years ago when I was working in banks, we had our servers and they were lovingly looked after like treasured pets, and we would upgrade them. We'd apply OS patches, new software versions, and we would upgrade them in place, which means that the state of the server was mutable. It changed over time. Um, that's not how we do things anymore. These days, we produce a container image, we ship it, we run it. If for whatever reason it doesn't behave the way we expect it to, or it's got a bug in it, or it's wrong, you shoot it in the head and you get another one. And
Yep.
those containers, those application images are immutable. They do not change once they've been created.
Right.
So
And if you need to make changes, what do? You create a new application image.
yes, absolutely. So that is what we have tried to do with Quarkus, and to think about this in the way that we have, to bring forward. Because if you just pop back to the last slide just a second,
Sure.
this one. Right. So what we've got here is we've got a lot of warm up and the building and the loading of the app. So things like constructing the dependency injection graph, making sure that it's valid, bringing those objects into existence, all of that stuff. It happens each time the application starts up, right? But what if we could add in process start, warm up, steady state? What if we can bring a new phase in between compilation and deployment, where more of that computation can happen? So this is sometimes referred to as shifting computation left. And basically, it's not standardized yet. I know we only have a few minutes, but we will talk about Project Leyden at the end.
Yep.
And within Quarkus, this is the way that we've chosen to do it, is to move as much computation as we can into a build phase where it's run once when the container is generated. So
Yep.
that's
Yeah.
there you can
It's
see that the app is being put into the build container much earlier. And then at that point, yes, we absolutely can deploy it in native mode. We can even go one step further and do ahead of time compilation to produce that super fast startup. But what we find with Quarkus is that in many cases, the majority of cases, I can't give you precise numbers, but I guarantee it's more than you're probably thinking. The shifting of computation into build time is more than enough for a sizable majority of customers. The extra complexity is worth it for some people, but you can do amazing things just by getting a lot of that reconstruction of the dependency injection graph and the generation, the spinning up of objects, and moving it into build time. So we
yeah.
see,
So just doing like some basic AOT and doing that stuff at build time, it just that alone provides a huge benefit in terms of application startup time and efficiency when you boot up. So yeah.
right, so we're not generating any native code here. What we're doing is we are just doing things like the resolution of the dependency graph. So basically, will this thing, is it guaranteed to wire up? Okay, great. Well, let's do that. Can we actually freeze and some serialize some objects so that they're just ready to go? Can we do things like use automatic proxies rather than like actually spinning up the network connections directly? There's all sorts of tricks we do. We've got our own dependency injection framework called Arc, which has been designed specifically for this use case. So that's basically how we do it. There are
Mhm.
other approaches as well. I mean, I know that Spring Native are having some good success as well, but they are very much focused on the native route for that. Whereas we want people to be productive, we want people to come to Quarkus because they enjoy working with it. And I think that if folks haven't tried it out, then even if you can't use it directly at work, just try it out with some home projects, because most of the people that I've spoken to who've tried Quarkus absolutely love it. It's such a nice fast development loop. It's got all of the things you want. We talk about developer joy, and I really do see it when I talk to some of our users.
Yeah, absolutely. I know when I first started playing around with Quarkus, in the basically when it first came out, the ability to just have the Quarkus running in dev mode over here, you write some Java code, you save it, and just magically, like, you don't even have to restart anything. You just reload. Like if you're working on a RESTful application, you just reload the RESTful endpoint, and boom, all your code is just there. And you can see in the log file where Quarkus is taking your source and compiling it and then injecting it live into the thing. For me, that's what really like got me thinking about, wow, this is amazing that we can do this kind of really fast iterative development without having to restart anything. Right? It's like boom, boom, boom. Right? So.
Yeah, I mean, I think we both remember the bad old days where you make a change, you redeploy, you go and get a cup of coffee while the application server restarts.
Or lunch, for that matter. Sometimes it took a long time for that thing to start if it was giant monolith, right? So yeah. Anyways, let's shift gears and talk about the future, Ben, and
Yeah.
Project Leyden. So this is a project. This I think actually Leyden's been around for a little while. I think maybe 3 or 4 years ago the initiative for this was kicked off. Um, and one of the kind of key things on here, then when Ben and I were talking about this presentation, and we're looking at the ahead of time compilation, like kind of how it's done today. And Ben very aptly mentioned that one of Project Layton's goals is to do intelligent ahead of time compilation. So why don't we start there, Ben?
Yeah, sure. So again, this is the idea of shifting compilation earlier in the process. It's about sometimes people call it shifting left. Um, and Project Leyden, it by the way, the name comes from, it's named after the city in, I'm going to say the Netherlands. I think it's a Dutch city, and it's named after what's called a Leyden jar, which is it's one of the early forms of what we would now call a capacitor. So the
Mm,
image that people should have is kind of like you're capturing lightning in a bottle, um, and that is the metaphor is it's the dynamism of the platform. You're choosing how to constrain the dynamism. You're choosing how much of the Java platform's natural dynamic nature you are prepared to sacrifice in order to get some other things that you want. And again, this is supposed to be flexible. It's supposed to be user determined for individual teams and individual applications to make their own decisions about it. So to give you one example, I don't know if people have poked around at the bytecode and looked at how Java lambdas are represented, but they are constructed using a technique called invoke dynamic. Um, you might have thought that when you make a Java lambda, you're making a tiny inner class. You're not. What happens is the body of the lambda gets turned into a private static method, and then there is some special linkage which takes that and generates a little class which has access to call that private method, which is generated automatically by the JVM at runtime. So the content of the Lambda body has been captured, but the linkage is generated at runtime. Now, for something like native compilation, you don't want to do that. You want to actually resolve all the lambdas at compilation time. And that transformation to say, no, actually, we don't need to re-resolve all of these dynamic call sets at runtime. We can actually apply this transformation to take the code which has the dynamic call sites to turn them into one which has statically resolved lambdas. We can do that at build time. So that transformation of taking the whole application state and transforming it in some way. The word that Brian and some of the other folks in Project Leyden refer to it is as a condenser. So a condenser is a whole program transformation which does this type of static analysis, takes then instructions from the application owner as to what transformations are acceptable and what aren't, and then from that can change the application to reduce its state. You know, you could switch off reflection completely. You could disallow dynamic class loading. So we talked earlier about the concept of the closed world for AOT compilation. That's a
yep.
very extreme constraint, and that's not going to be acceptable for a lot of applications. If you are in that world and you want the performance that can be got by accepting those constraints, that's fine. But you don't have to. This is supposed to be about enhancing choice, but being able to do so in a very controlled and a very fine-grained way.
Yep, absolutely. And there's a few other parts. I don't know which one of these we should dive into more. Trying to remember what the some of the class initialization stuff in Leiden is. There's three bullets here,
Mm.
obviously. Handle class initialization at build time. Do we does Quarkus do some class initialization and some kind of like pre-optimizations at build time, Ben?
Yes, it does. But
Okay.
the key thing here is that Quarkus doesn't do that in a standardized way because the standards don't exist yet, right? So what we want with Leyden is to see it develop in a way which is compatible with all the existing Java applications. And I mean, I can't speak for the Quarkus team, But I would anticipate that we would want to align with whatever standards come out of the Java process. And as Red Hat is a contributor, I would think that we would take our ideas and and collaborate with friends and peers at Oracle and elsewhere within the OpenJDK community. But the key point here is that it has to become a standard. It has to become a recognized part of the Java platform and the VM spec and the language spec.
Yeah, absolutely. So I think that this may have been something that we glossed over. So just for the audience, to let them know, Project Leyden is is something that is part of the Open JDK process community, whatever you want to call it. So it's not just something that's over here worked on the side. As Ben mentioned, Red Hat is part of OpenJDK, as is Azul, and other folks who contribute into OpenJDK. So this is very much a Java community focused effort. Obviously, the Java team at Oracle is driving it, but it's not happening just by them. It's a community effort by a bunch of different companies, and of course it will hopefully become a standard that the different JVM vendors like Red Hat and Azul can build on top of, on top of OpenJDK, on top of that, to do
Yep.
interesting and fun stuff.
Yeah, I mean, the way that I would always explain it is that there are short-term efforts which are about delivering an individual feature, whether that's a language feature or a VM feature. And then there are these long-running, and by long-running, in most cases, I mean multiple years, research efforts to produce a major, not just feature, but potentially even change in direction. So a good example would be something like Project Lambda, which produced
Mm,
Lambdas back in Java 8. We also have Project Amber, which gave us things like local variable type inference. There are also things, and also
Valhalla.
now, yeah, and pattern matching, and that now Valhalla, which has still not arrived yet, which is about can you fundamentally change the low-level data model of Java. It's one of the most impressive re-engineering efforts I think I've ever seen. Um,
Mm.
so Leyden should be seen in that context. It's a long-running project. It is changing the very nature. It's introducing this idea of composable transformations on whole programs, about being able to choose which constraints you accept, and potentially also introducing concepts like that we already see in Quarkus, of there being additional phases to the Java application lifecycle that until now just haven't existed, and doing that in
Yep,
a standard way.
absolutely. Absolutely. So and you just mentioned that Valhalla, Amber, all those are long running projects, and Valhalla is still ongoing. So when you think of Project Leyden, we're probably still a couple of years or longer away from seeing some of the fruit of this effort come into OpenJDK and the Java virtual machine. What are your thoughts, or how do you kind of, if you had to, I know it's impossible to pin something like this down precisely, but how long do you think before some of these things start to make its way into OpenJDK, if you had to speculate?
Right. So I mean, I think I hope everyone knows there's a new release of Java every 6 months, and currently every 2 years we have what's thought of as an LTS release.
Yeah.
I don't want to get into to the details of that, but
Yep.
broadly, those are the releases that people tend to cluster around. So the last one was Java 21. So in September of this year, we will see Java 25, and if the same pattern continues, which it may do and it may not, but assuming that it
Yep.
does, that would be the next release that we would expect to see a large uptake in. Um, will we get some things from Leyden in 25? We might get some.
Okay.
Um, Basically, the way that it works is about 3 months before the release is the feature freeze. So at that point, you've either made it into the release or you've missed the train. So by about June of this year, we should know what, if anything, from Project Leyden is sufficiently mature to go into Java 25. And then I would expect, if I'm being optimistic, maybe we'll get a couple of small things. But I don't expect the majority of the work to land in time for 25. I think it's much more likely that some of these things will trickle out over the next few releases, and maybe we'll see more in September 2027.
Right. When the subsequent LTS release comes out.
Right, but I'm always reminded of the words of James Gosling, the creator and the father of Java, who said that it's better, if you don't know the right thing to do, it's better not to do anything than ship something and regret it. So
Yep.
that's part of the philosophy of Java. It always has been. Java is a small c conservative language. Um, we don't make changes that are in haste and regret them later. Better to wait. Better to think things through. Even if people then complain about the language moving too slowly.
Yeah, absolutely. Java has incredible track record for, backwards compatibility, for example, and, well, backwards and forwards compatibility, and being rock solid. Of course, everyone knows that the world runs on Java, whether it's banking or, whatever. The world runs on Java. So being conservative in certain cases is good, right? You want your code to be able to run with new versions of Java, and when you write, Java code in use new features like records and seal classes and things like that. You want the comfort of knowing that it's been well thought out and that you can use it, you won't have problems and stuff like that. So not edge cases and stuff like that. So
Yeah,
anyways,
I
let's sorry, go
Are
ahead.
we, no, I was just going to say. I mean, I think we're probably close to wrapping up, but
Yeah.
I would always describe that as some people sometimes call Java the best language for weekend orientated development. Because you're going to build a robust production system, and you're not going to worry about it breaking on your weekend.
Right, right. Nice, nice. Absolutely. All right. So, Ben, thanks again. Let me flip back real quick. Check out Ben's new book, Optimizing Cloud Native Java. I read the book. I got a review copy of it a while back. I read it. It's a wonderful book. Had lots of good nuggets of information. And also, don't forget to download our cloud cost optimization or our Azul performance high performance computing, high performance Java guide, which is also on the screen right now. And Ben, thank you so much for joining us today and for
Thanks for
sharing
having
that
me.
information. We had a good had fun chatting about all the nerding out about all the cool Java stuff that's happening, and we'll look forward to having you back sometime soon. Thanks so
That's
much.
great. Thanks, Pratik.
Yep. Take care.